So for today class, we're going to learn how to determine first an exact differential equation, or specifically a first order exact differential equation. Then after such, we will learn how to find its solution. Now, let's say, for example, the form of your differential equation is something like this. You have two terms, and you have the differentials of x and y. And in those differentials, you have functions of x and y, or either a function only of x or only of y as their coefficients. So these are the coefficients of your differentials. The coefficient of the differential of x is m, and the coefficient of the differential of y is n. So I said a while ago that it could either be a function of both x and y or just one of those two variables. Now, there is this theorem that if m and n and the partial derivative of m with respect to y and the partial derivative of n with respect to x are continuous functions of x and y, then there is a necessary and sufficient condition that the m of dx plus the n of dy is equal to 0 be an exact equation is that your partial derivative of m with respect to y and your partial derivative of n with respect to x should be equal. Now, the last relationship that you are seeing in this page tells you of the testing for exactness. So to test whether your DE is exact or not, it's important that you know how to partially differentiate a particular function or expression. So as you can see here, you will be getting the partial derivative of this m here. You're going to differentiate it in terms, or partially differentiate it in terms of y. So it's the other variable, because you can see that your differential here is in terms of x. So you will partially differentiate m with respect to the other variable y. You do apply the same procedure with n, but you will partially differentiate it with respect to x. Why? Because the variable that appears here on your differential is y. Okay, so then this is a needed requirement that the partial derivative of m with respect to y and the partial derivative of n with respect to x should be the same, exactly the same, including the signs. Okay, if not, then your D is said to be inexact or not exact. And there's a procedure on how to make it exact, and we will learn it in the next meetings. So for this afternoon, we will just handle exact differential equations. So as a review, when you do partial differentiation, you consider the other variables that appear in your expressions as constants. So if they stand alone, their derivative should be equal to 0. Okay, so let me clear this page and we will proceed with the next. So this is the testing for exactness. Now, the differential equation then, so you have already tested and it came out that your DE is exact. So the differential equation of the form m of x and y dx plus n of x and y dy being equal to 0 is an exact differential equation if there exists a function f of x and y. So this is now referring to the solution of your exact DE such that the differential of that particular function is equal to the m of x and y dx plus the n of x and y dy, which is said to be 0. Now, as for the solution, I'd like to go back in the previous page. This is your testing. So when you tested and this is true, then your D is exact. How do you find the solution? So it will require these two relationships that you will need to partially integrate. Okay, what are these two relationships? Remember that this f is already representing the solution of your differential equation, which is said to be exact. And this partial derivative of f with respect to x is actually equal to the m here that appears on your original differential equation. The m, that is the coefficient of the differential of x. Now, the coefficient of the differential of y, which is n of x and y, is actually equal to the partial derivative of your solution f with respect to y. So I said you're going to partially integrate these two. So what do I mean by that? You need to transfer this partial differential of x in here. The same thing with this partial differential of y in here. So what you will see actually is something like this. And another one in here. And you need to integrate this. Now, when you integrate these two, you will be forming two separate expressions. So let's say I will have this as F1. Sorry. Will not label that as F1 because that's still your F. So that's F1 and this one is F2. So when you partially integrate M, you will consider Y as a constant and you will have a corresponding expression here. And the same thing in here, you will have a corresponding expression here. And how you treat these two to come up with the solution of your exact differential equation depends on what particular method you're going to use. And for today, you're going to learn 3 different methods of finding the solution of an exact differential equation. And we will go through each of those one by one. Okay? So let me go to the next page. Now, method 1. Method 1 class is the easiest of the 3, okay, because it's straightforward and you can right away pick the terms that will be appearing in the solution of your exact DE. What you need to do is to integrate the partial derivative of f with respect to x. So you're going to integrate this partially with respect to x, holding y constant. And you will get an expression of f. Okay, that's, let's say, your F1. And you will also integrate the partial derivative of f with respect to y, holding this time x constant, and that's your F2. This method, being straightforward, only requires you that you compare the two f expressions, F1 and F2, and then copy the terms that appear on them. If there's a common term that appears in both F1 and F2, you don't add them, you just simply copy them. But nonetheless, all terms that appear in both F sub 1 and F sub 2 should be represented in the form of the sum of terms in the solution of your exact differential equation. Okay, to illustrate what I mean with this, I think that, as I've said, this is straightforward. It's easier than the next two methods. We'll have the first example. Now, you are to solve the differential equation 2xy dx plus the quantity x squared plus 3y squared dy equal to 0. Before you are even tempted to solve this using the exact differential equation technique, there's a need for you to test. And the test is always a requirement. And what do you test? You test whether the partial derivative of m with respect to y and the partial derivative of n with respect to x would be equal. So this is actually your m and this is actually your n. And as you can see here, what's being done is you partially differentiate 2xy, your m, with respect to y. So you consider the x as a constant, just like 2. So the partial derivative of 2xy with respect to y is 2x. You apply same principle to the partial derivative of n this time with respect to x. Y is a constant, so the derivative of the second term here will automatically be a 0. So x squared will have a derivative of 2x. Now you see the 2 being equal, so we can conclude that our DE is exact. Since it is exact, then in this case, for this particular example, we will use method 1. So method 1 very simply requires you to partially integrate m and n with respect to x and y respectively. So meaning if there are other variables appearing on these two functions, as you could see, it's a mix of x and y, you will consider that particular variable a constant. So when you integrate, in this case, 2xy with respect to x, to get one f expression, then you consider y as a constant. So you're only integrating x here. And if you use power rule, that will be x squared over 2, explaining why 2 is gone already in here. So this is one f expression. Applying the same principle for your n of x and y, which you will partially integrate with respect to y, considering x a constant. So if you integrate x squared with respect to y, with x being a constant, you will have x squared y. If you integrate 3y squared, then that would be y cubed, because the 3 will cancel with the 3 in the denominator of y cubed. So as you could see in here, your 2f's has a common term in the form of x squared y. And you have one uncommon term, y cubed. So when you write the solution of your exact DE, you copy the terms, as in my term is you copy. You copy the terms that appear in both f's that you got out of your partial integration. If there's a common term, you just simply copy it once. You don't take the sum of these 2x squared y. So if copied, you have it here already. And this one, which is not uncommon, you also copy it. Example, class, you have here minus 2x. See, since you have here a minus 2x, which is not common for the 2f's, you also need to include, you place here minus 2x, in the solution of your exact DE. So all the terms in your f expressions should be well represented when you write the solution of your exact DE. So the term is copy. What you copied, you add. So this is minus, so it should be minus here. These two are all positive, so you place here positive. But you don't add the commons, you just simply copy. So it's very straightforward, and it will eliminate errors due to like integration and partial differentiation in the process. So in finding the solution using method 1, you only need to partially integrate, because the testing class is prior to finding the solution of your exact DE. So you have to really test first for exactness, then afterwards, then you are free to use the methods that you can choose from, that you're comfortable in using. Okay, now I will clear the drawings in here. Before I go to the next method, do you have any questions so far?
Miss, question ka tanit, Miss.
Yes.
May ara, Miss, shortcut nga imbis nga masolve ka sa duwagid ka F. May ara shortcut nga daw mas mapadali pag nga instead of solving duwagid ka F.
You have to solve for both. You have to solve for both. Yes, because the other two methods are even longer. Unless otherwise, you have come up with a resource material in which there's only one solution. But so far, in 20 years of teaching DE, more than 20 years of teaching DE, this is the shortest method that I have presented to you. Method 1.
Miss, thank you, Miss.
Okay, Bobby. Some more question? Okay, we go to method 2 then. So page 2. Method 2 rather. So in here, you also have a 2-step procedure in finding the solution of your exact DE. This is after you have already established exactness. So integrate. So you have done that in method 1 as well. Integrate the partial derivative of f with respect to x. This one is actually your m. And you need to integrate it with respect to x holding y constant. In the process of integrating, you will get this expression. So your f is equal to the integral of the m that is written as the coefficient of the differential of x in your DE, plus instead of an arbitrary constant c, you have this g of y expression. This g of y class is a function of y. And how do we find this one? Because this one will yield an answer because you are going to integrate partially with respect to x, holding y constant. So you will have a specific answer here, and you will have a g of y in here. So you cannot write the solution of your differential equation with a g of y, because when we speak of g and y, it's generic. We don't know what it represents. All we know is that it's a function of the variable y. So how do we get g and y? You proceed to the next step. This answer that you got here in step 1, you differentiate with respect to y. So whatever is the expression that you have here, you differentiate it with respect to y. Your answer, the derivative of that, should be equated to n. What n means? The n that is the differential of your, that is the coefficient of your differential of y in the given differential equation. In the process, you will have this particular expression, which will lead you to the g of y. Once you have the g of y, you go back here and substitute this g of y in here in your answer, and that would be now the solution of your exact differential equation. Okay, so for you to understand this better, we'll go to a specific example. Okay, you could see in here, I'd like to copy the DE in here because it's cannot be seen later on. So you have 3x xy minus 2 dx plus 2y dy equal to 0. So this is our original DE. Okay, what we did is we expanded this one, so we'll have 3x squared y minus 6x dx plus 2y dy equal to 0. With this one now expanded, it's clear that this is your m and this one is your n. Now, so you do the testing before you apply the procedure. So when you differentiate this one with respect to y, your answer is 3x squared, because this one is a constant. So that would be 0. This one is differentiated in terms of y, that would be 3x squared. Now, if this is differentiated with respect to x, then this one is a constant. So the derivative is 0. This one will lead to 3x squared as the derivative. So the two being the same, now you are sure that your differential equation is an exact differential equation. So we do the first procedure. You partially integrate m. That is your partial derivative of f with respect to x. So when you integrate it with respect to x, you consider y as a constant. So the resulting expression class would be this. So this one, integrated with respect to x, will yield x cubed y. How is that, miss? So you will have here, so you have here partial differential of f is equal to 3x squared y minus 6x. And we will transfer the partial differential of x here on the right side from this one. Then you integrate. So when you integrate, your y is a constant. This one will be integrated. So the answer is x cubed y. In here, if we integrate, this would be 6x squared over 2. So that would be 3x squared. And you will have this constant of integration g of y. This is actually already the terms that appear in the solution of your DE. But you are required to find the g of y. How do you find the g of y? The answer that you have here, you differentiate with respect to y. So the answer that you got in the first step. So if you differentiate it with respect to y, so in here in the second step, you will have partial derivative of f with respect to y is equal to, so if you differentiate with respect to y, then this would be x cubed. This one will have a derivative of 0 because your x is a constant. And this one, since it's a general representation of a function of y, will be simply g prime of y So that is why you see here that the partial derivative of f with respect to y is x cubed plus g prime of y. We have partially differentiated your answer in step 1 with respect to y. What you do next, you equate it to the n. What's the n? That would be the n in your, where is that? X cubed plus 2y. Your n, which is x cubed plus 2y. Why is it now x cubed plus 2y? Let me close class so I can see. This is your n. Okay? X cubed plus 2y. I only wrote here 2y, by the way, so that is why I was quite confused. This should be x cubed plus 2y, Arakas. So I have copied, I lack x cubed in what I copied. So plus, you have your x cubed plus, okay? So that's it. So you can see here, that's our m. So we equated our partial derivative of f with respect to y to the n. In the process, you can cancel the x cubed and you are left with g prime of y to y. We don't need g prime of y, we need g of y. So you will need to integrate both sides of this equation. Okay, so when you integrate, this will lead you to y squared. This is already the g of y that should be appearing here. So the solution of your DE will be now this one. X cubed y minus 3x squared plus the g of y that you got in step 2, y squared. So when you write your solution, class, you don't write f of x and y equal to, you just simply write x cubed y minus 3x squared plus y squared equal to c. So this is now the solution of your exact DE using method 2. Okay, so before I go to method 3, do you have any questions? Okay, so majority of my students before doesn't like this method because aside from the fact that you're going to partially integrate what you answered, you will partially differentiate and then do the equating and then integrate again. So it's quite lengthy in terms of the procedure, whereas method 1 is more straightforward. But there are differential equations, first order differential equations that are exact that could be solved more accurately using this particular method. Okay, now let me clear this one and we go to method 3. Method 3, class, in principle is comparable to method 2, only that we didn't integrate partial derivative of f with respect to x, but partial derivative of f with respect to y. But in principle, what is used is the same exactly as method 2. So you are to integrate the partial derivative of f with respect to y, and this is actually your n. So you will integrate it with respect to y holding x constant. In the process, since it's x that is held a constant, your arbitrary constant of integration will not be any more g of y because x now is the constant. So this is now your f of x, replacing the arbitrary constant c. Okay, so step 2, just like method 2, would help you find out the f of x by differentiating your answer here, f, with respect to x, and then equate it to m. So in method 2, you differentiated your f with respect to y and equated it with respect to n. This time, it's the other way around. The process is still the same, having the same goal, and that is you solve for the function of x, which will replace this one, the f of x expression in step 1. Okay, so we will now apply this same principle to our differential equation. So let's say we're still going to work on the same DE, but this time we will use method 2. So it's, I'll write here, class, the expanded form. So 3x squared y minus 6x dx plus x cubed plus 2y dy. So this should be equal, the sum of these two should be equal to 0. So let me just, okay, to check. So x cubed plus 2y. Okay, so this is our DE. The DE where we used our method to a while ago. But this time we will partially differentiate, or partially rather integrate your n, which is the partial derivative of f with respect to y. So this is your n, and it's in here. If you integrate it with respect to y, you will have in here x cubed y. So I will write in here so it would be clear. So you will have partial differential of f, and you have x cubed plus 2y to y. Okay, we will integrate. So you will have an f, which is equal to, you have x cubed y plus y squared. Your arbitrary constant of integration will be a function of x because we considered x as a constant. So that's the function of x. So you see this? This is your function of x here. What will you do with this? This is your step 1. Your step 2, you will partially differentiate the f that you have here with respect to x. So if you do that, you will have 3x squared y. This one would be 0, so you will have f prime of x. This is a 0 because that's a constant and you're partially differentiating in terms of x. So this you will equate to m. So what is the m? Your m is this one. So you will equate it to 3x squared y minus 6x. In the process, you get to cancel this one, and your f prime of x is equal to negative 6x. As you could see here, you need to integrate this to get f of x, which you will substitute in here or in here. So that would be negative 3x squared because you will have x squared over 2. So your 6 will be divided by 2, giving you a 3. So knowing your function of x is negative 3x squared, you can go back here in your original expression in step 1 and substitute it. This is already the solution of your exact differential equation using method 3. Any question? Okay, so no more question. Okay, what if this particular differential equation we will solve using method 1? Which do you think will arrive at the answer quickly? So let's I'll share Jamboard to you. That way we can write our solution there. Okay, wait class. Okay, I'll stop sharing for now. And let me check if I can use Jamboard. So what if we use method 1? So I'll write here the expanded form. Do you see the Jamboard? A reaction, please, if you could see the Jamboard.
Yes, ma'am.
Okay. So you will have 3x cubed y minus 6x dx plus x cubed plus 2y dy equal to 0. Let me check class in the PowerPoint if this is really the m. X squared minus 6x x cubed plus 2y. This should be x squared. Okay, we should have the same given. So 3x squared y expanded already. This is our DE in method 2 and 3. So what is required in method 1? You will integrate this one with respect to x. So you have partial differential of f equal to 3x squared y minus 6x. Partially integrate with respect to x. So your f is equal to x cubed y minus, so that would be 3x squared. This one, on the other hand, partial derivative of f with respect to y, we integrate this partially with respect to y. And your f here will be x cubed y, and you will have here plus y squared. So you could see that these two terms are common, and you have these two which are not the common terms. So what you do, you just simply copy the terms that appear in both f. So you have x cubed y minus 3x squared plus y squared equal to c. This is the same solution that we got in method 2 and 3. So if you take a screenshot of this, so x cubed y minus 3x squared plus y squared. Let's check if it's the same as our in the PowerPoint. Okay, x cubed y plus y squared minus 3x squared is equal to c. So the same. So as you can see, using 3 different methods for one particular differential equation points out to you that method 1 is really more straightforward than the other two. But as I said, I presented this to you because in our book by BDN and Rainville, methods 2 and 3 are the ones that are being discussed. So method 1 is just a shortcut actually of method 2 and 3. Kay Bobby was asking a while ago, may shortcut pagid mi sa method 1 na shortcut na siya gani. Kay ang lawig, amo na siya ang ginadiscuss sa atong gidya nga textbook. So during pre-COVID times where we are requiring students to have a copy of the textbook, if they don't have, you just make sure that they have a soft copy of that because we give assignments that are found in the textbook. And the procedures that are discussed in the textbook are these two, either method 2 or method 3. So do you have any question, class? Do you have any question as to the finding of the solution of an exact differential equation? Any clarification that you'd like to raise? The challenge your class is this, with exact differential equation, you have to practice partial differentiation and partial integration. It requires integration and differentiation, partial that is. So the tools that are needed are assumed to be, should I say, mastered by the students who are already enrolled in this subject. So the example that I'm giving you here is simple because they're just using power rule. So what if the coefficients or the example, the problem, the differential equation that is given to you is, in the, let's say for example, has trigonometric functions, exponential functions, or logarithmic functions. It's a different story anymore. The examples that we're given here is just for illustration purposes. So you are to, of course, you are required to go beyond what is given in class. That way, you also build up your knowledge on how you're going to apply and make use of the principle that was illustrated by the use of these simple examples. Now, having said that, class, so do you have any question here before I stop sharing? Okay, none. So I'll stop sharing. I'd like to go first to the chat box so I can see it will be reflected in the recording who are present this afternoon. So we have Eloterio Rivera, sabay-sabay. Esparagosa, Ledesma, Alvarez, Gio, Paredes, Pabuaya, Aujero, Lumawag, Bacolod, Quadra, Ofelenia, Jambunganan, Cabiles, Gamao, Maravilla, Singhed, Romero, Gan, Santiago, Mirasol, Peñalosa, Losada, Cabugwas, Bailon, Dumayan, Abong, Awakay, Tinanaw, Demaranan, Escobar. I hope I have mentioned everybody who are physically present in this Zoom meeting. Okay, I will close now the chat box and I will stop recording.